Scientists looked for new space-time structure deep under the South Pole in Antarctica, and this is what they found. The icecube neutrino observatory under the South Pole probes space-time using ghost particles, quote-unquote, and scientists have just published a study on their work. Scientists peered into the structure of space-time to look for new physics that might be written into the signatures of elusive ghost particles with the help of a gigantic observatory that extends nearly a mile under the South Pole, reports a new study. Though this year's long experiment did not find any new physics imprinted in these spectral particles known as neutrinos, it still represents an unprecedented glimpse into shadowy realms of the cosmos that have remained out of view until now. In particular, the new research sheds light on the quest to describe gravity using quantum mechanics, because this so-called quantum gravity is a major key to unlocking some of the biggest mysteries of the universe. The icecube neutrino observatory, the largest neutrino telescope in the world, has been operating for a decade at the South Pole. The detector is made up of thousands of sensors that reach some 2,500 meters beneath the Antarctica ice, about the length of 28 football fields, where they capture energetic neutrinos that originate in explosive events from the edge of time and space. Now, the icecube collaboration, a team that includes more than 400 scientists, has announced the results of a search for a new space-time structure that probed regions of the universe that were previously inaccessible to human technologies, according to a study published on Monday on Nature Physics. The icecube is really special because it can see neutrinos coming from really far away and with really high energy, said Tepi Katori, an icecube team member and an experimental particle physicist at King's College London, as well as co-author of the study in a call with Motherboard. We use these two properties, that neutrinos can travel the longest distance in the universe and at the highest energy, he continued. It's a big assumption, but those particles are believed to be very sensitive to anything within space-time. Neutrinos are so lightweight that their masses are almost imperceptible, earning them the nickname ghost particles. For this reason, they're able to effortlessly pass through planets, stars, and other forms of matter without slowing down or changing direction. This makes neutrinos very difficult to detect with conventional instruments, even though they are so abundant in the universe. At about 100 trillion of them pass through our body every second. Every second, 100 trillion neutrinos pass through our body. That's amazing. Most of the neutrinos around Earth are shot out by the sun, but there is another class of high-energy astrophysical neutrinos that come from pyrotechnic objects called cosmic accelerators that are located many billions of light years from our Earth. These accelerators could be objects such as blazars, which are galactic centers that blast out jets of light and energy, though the exact sources of astrophysical neutrinos are still unknown. Neutrinos come in 3 different flavors that are associated with fundamental particles in the universe called electrons, muons, and taus. Scientists have long suspected that changes in the flavor of astrophysical neutrinos could open a window into regions of space-time that may defy what's known as Lorentz symmetry, which is an important bedrock of Albert Einstein's special theory of relativity. Lorentz symmetry essentially means that the cosmos should look the same to 2 observers that are traveling at the constant speed relative to each other. In other words, the universe at large scales is basically isotropic and homogeneous, even though it appears more varied at smaller scales, including the planetary perspective we experience as humans on Earth. Researchers are obsessed with detecting violations of this symmetry because they might expose the long-sought missing link between gravity and the standard model of particle physics that governs quantum mechanics. For the last 100 years, people have tried to find evidence that Lorentz symmetry is not true, and no one can find it, Katori says. This is one of the most traditional studies of modern physics, people challenging this space-time theory. If something is wrong in the Lorentz symmetry or something is beyond the Lorentz symmetry, you might have some connection for the first time to gravity in the standard model, he said. Quantum gravity is something many people are hoping is really the next generation or an open door to the next stage. Astrophysical neutrinos offer a promising test of Einstein's theories because they might encounter unexplored regions of space-time that are affected by quantum gravity. Neutrinos that pass through such areas could potentially switch flavors in surprising ways that would leave a record of space-time anomalies in their signatures that could be read by scientists that capture them on Earth. Neutrinos switch flavors, even without this space-time effect, Katori said. We are now looking for anomalous changes or unpredicted ways to change. That's the focus of this research. IceCube search found no anomalies in neutrino flavor conversion, leaving the notion of Lorentz symmetry intact for now. While Katori said these results were somewhat disappointing, who would not want to find new physics after all? It's still an important finding. IceCube was able to unambiguously reach the parameter space of quantum gravity motivated physics, according to the study. Put another way, the results have blazed a new trail into the theoretical domain of quantum gravity that will have all kinds of applications for scientists across the fields. We believe these are great results, Katori said. We have the highest sensitivity, and we are also the first experiment to reach some region or phase space, the technical word, to really look for it, referring to the Lorentz symmetry violations. So I'm so relieved that this is finally published, he said, from data taking and other issues that it's just such a long effort. Even as this initial experiment comes to bittersweet end, a new beginning is emerging under the Antarctic ice, as well as from other instruments around the world. The IceCube collaboration plans to scour their data sets again, using new machine learning techniques that might be able to pinpoint anomalies that were missed in the study. The team also hopes to dramatically expand the size of IceCube in order to obtain an even bigger data set that might at last reveal traces of space-time anomalies that point to quantum gravity. Katori said, in my opinion, there's still a chance. This analysis is the first iteration of this type. We made this an analysis framework and developed the code, but in some sense we did not do the best of the best because things are still developing. I believe there's a chance to improve it, he said, but I can't guarantee how much. In the meantime, the new results show that it's possible to probe space-time itself using slippery particles from the distant universe, providing a way to explore a host of other potential models and experiments. Although the motivation of this analysis is to look for evidence of quantum gravity, the formalism we have used is model independent, and our results can set limits on various new physics models, including a new long-range force, neutrino dark energy coupling, neutrino dark matter scattering, violation of equivalent principles, and so on, the IceCube collaboration concluded in the study. And this is on Vice by Becky Ferreira. Please leave your comments. Thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box